Hello everyone and welcome back to the channel. Today we'll be talking about wormholes. So let's start off with some This Week in Astronomy as always, looking at the James Webb Space Telescope first. Recently the James Webb Space Telescope took a really nice looking photo of Titan that looked at some of the clouds and some of the atmospheric hazes around Titan. And this is just an image that is comparing those of Titan to those of Earth, which is really cool. As some of you may know, Titan is thought to be the next most habitable place in the solar system right after Mars, and so eventually, after the sun turns into a red giant, maybe we'll look to settle on Titan instead of Mars. Next is the image of the closest active galactic nucleus, which is thought to be powered by a black hole with a mass of approximately 100 million solar masses. So this is the AGN, which is powered by a black hole in the center. And these AGNs are super bright because of the black hole's accretion disk, which we'll talk about a bit more later. Now let's move on to the Hubble Space Telescope. So the Hubble views a star-studded cosmic cloud. I don't know, the photo just looked nice. The Hubble views a celestial fireworks display. This is also a really nice looking photo. Finally, let's talk about wormholes. Now, contrary to what you might have seen in movies like Interstellar or Arrival, wormholes aren't real. They haven't been even experimentally proven yet, much less observed. But the math does seem to check out for a couple of models of wormholes. So they're definitely interesting to talk about, and let's dive into some of they are. So, what are wormholes? A wormhole is a hypothetical structure that connects two very distant parts of space-time. Wormholes can span light years, a few feet, or even separate universes. Again, this is all extremely theoretical. Wormholes aren't real, but some of the models that we've derived, for example, like Einstein-Rosen bridges, some people think that they might be real, and if they are, wormholes could be able to span very, very different parts of space-time. Now, we all know that trope in a movie whenever someone's talking about a wormhole. Um, they tend to use a sheet of paper and stab a pencil through the paper after folding it to sort of display the wormhole, and that's not too far off, but that is more of an archaic view on what we think of wormholes to be. Um, that's definitely one of the older theories of wormholes. That's what we call traversable wormholes. They have been mathematically disproven. Um, not really disproven, but just the circumstances for their existence would be near zero. So let's talk about the first wormhole. The German astrophysicist Schwarzschild was the first to postulate about the existence of wormholes. You might remember Schwarzschild from things like the Schwarzschild radius of black holes. So yeah, overall just very influential astrophysicist. In his model, which was called the Schwarzschild wormhole, it consists of one singular black hole, a white hole, and a long tunnel that connects the two. Uh, so we all know what black holes are. They're points of infinite densities, and uh, they cause massive dips in space-time. Um, and white holes are sort of the opposite, where a black hole causes a funnel in space-time. White holes, which are thought to be made of negative mass, cause a bump in space-time. So they actually eject matter instead of sucking them up like black holes do. Again, this is all extremely theoretical. I'm assuming the math checked out when Schwarzschild was making these calculations, but as I said before, none of this is absolute. But this is what your classic wormhole looks like, where a piece of matter travels through the event horizon of the black hole and out the event horizon of the white hole. But they are more archaic, um, and scientists have moved on to more complex theories of wormholes. Uh, so the next most widely regarded model of wormholes that is still being used today are those of Einstein-Rosen bridges. They are the most mathematically sound postulation developed in the 1940s by Albert Einstein, who we all know, and one of his physicist friends, Nathan Rosen. Um, so in this model, the wormhole consists of two black holes that are quantum entangled. Uh, so that means that perturbation of one causes an identical perturbation in the other, no matter the distance between the two. Quantum entanglement is a complex phenomenon, which I'm not going to get into too much detail in this video. But pretty much, if two pieces of matter are quantum entangled, no matter how far apart they might be in the universe, any sort of change in one can also be observed in the other, and it's the exact same. So, in Einstein-Rosen bridges, the singularities of both the black holes are quantum entangled, uh, and therefore they cause this bit of a funnel in the four dimension of space-time. This theory has persisted for as long as it has because of how much it makes sense. And one thing to clarify is that these Einstein-Rosen bridges are not traversable, and we'll get into a bit more of what that means a bit later on. So this is what the Einstein-Rosen bridge tends to look like. This is again your typical wormhole looking illustration because it is the most popular. In the middle we have the throat, which requires negative energy density, and you have two mouths on the outside. So theoretically, instead of light having to travel whatever X light years from point A to point B, light can just traverse through the wormhole, through the throat, go in from one mouth and out the other, and reach point B in a fraction of the time. So let's talk about traversable black holes. Einstein-Rosen bridges and Schwarzschild wormholes are not traversable, meaning that matter cannot pass through them and come out on the other side identical. When Einstein and Rosen were devising their model, they realized that for a wormhole to be traversable, it must have negative energy density. Now that might sound complicated, but negative energy density just means that an object must have less energy than the vacuum of space that's around it. And quantum mechanics has taught us that even empty space has some amount of energy in it. So achieving negative energy is theoretically possible. It's just extremely unlikely, and it's very difficult to procure. If humans could achieve negative energy density, um, they would have access to limitless energy, which is kind of cool. A universe with negative energy density at all points will either expand indefinitely or disintegrate in a big rip. And a universe with a positive energy density will eventually collapse in a big crunch. In a energy density universe like the one that we have, the amount of positive energy is in the form of matter and is exactly canceled out by its negative energy in the form of gravity. And this sort of ties back to Einstein's E equals mc squared equation. It's unclear which one of these models accurately describes the universe, but scientists, most astrophysicists tend to agree that we are currently living in a zero energy density universe. Now, finally, one more exotic theory of wormholes are those of exotic matter wormholes. Some have speculated that exotic matter with negative mass, could be used to traverse an Einstein-Rosen bridge. If there is enough exotic matter, it could counteract the downward curvature of the black hole with its own upward curvature, causing the bridge to be open for travel. Again, this is highly theoretical and not at all possible by current technology. That's that. That's all I have to talk about for wormholes. Thank you everyone for tuning in, and I'll see you in the next video.